So, in the chapter 5 so far, we've looked at objects moving in a perfectly circular path. Now we're going to expand that to a much bigger kind of scale, and we're going to look at the orbiting of planets and look at the gravitational force between two objects. But we're going to look at specifically Newton's universal law of gravitation, okay, or Newton's law of universal gravitation, however you want to say it. But essentially, what we're looking at here is he kind of was wondering, basically, why did the moon keep this circular orbit? What made it stay in that path, right? There's no friction. There's nothing like that that's holding it in its path. So he started to think about what is it that makes the moon completely stay in that circular orbit and not really stray, right? Because it's had a really consistent orbit since the beginning of time, right? So he wanted to see basically what was the reason for that. So the way that he did this is he started thinking about the gravitational force and how, he discovered gravity, or he conceptualized gravity to begin with. So he understood that if the Earth was able to pull things to its surface on the surface of the Earth, then it could surely pull the moon and keep it in its circular orbit. Okay, so that's what he started to look at and compare. Okay, the gravitational force that the Earth had on the moon. Okay, and he wanted to look at basically, was that gravitational force equal to on the surface of the Earth? Did it have a lesser effect as we get farther away from the surface of the Earth? That's what he was really looking for here. Okay. So when we talk about gravity on the Earth's surface, we know that the acceleration due to gravity at Earth's surface is 9.8. Okay. Do we expect the acceleration due to gravity to increase as we get farther away from the surface, or to decrease? Decrease, right? We talk about how on the moon there's no gravity, right? Realistically, there's gravity. It's just to a much lesser degree, okay? A lot less gravity. So that's why we see astronauts when things float, right? That means that force due to gravity is acting on them with a much less magnitude, okay? It's not really having that much of an effect. So there is a gravitational acceleration on the moon. It's just to a much lesser extent. Okay? So after comparing the radius basically of the Earth's surface and basically looking at how far away objects are from the Earth, he was able to derive a couple of these equations, okay? So he looked at the radius basically between two objects. And when we say the radius, we're realistically looking at the distance between two objects, the distance between the center of two objects. So he compared the radius and he compared the masses of these objects and the effects they had on the gravitational force, and he came up with this equation. Okay, so this equation needs to go on your equation sheet, and in your notes, we're going to use this a lot. Okay, so in this equation, we're still thinking about the objects in terms of the Earth being one object and whatever else we're comparing to being the second object. Okay, so M1 might be the mass of the Earth, M2 might be the mass of the other object that we're looking at, that we're considering. Okay, R is always the distance between those two objects. Okay, G is what we call the universal gravitational constant. Okay, and F sub G is our gravitational force. What do we know that Fg is always equal to? Mass times gravity. And we're going to be able to apply basically that same principle here too. We might have to do a substitution every now and then. Okay, but this is the same gravitational force that we always solve for, except now we've got a much bigger scale. Okay, so Fg is the gravitational force. Big G right here is the universal gravitational constant, and this value you need to have down in your equation sheet or in your notes or both, because we're going to use that value a lot. Okay, 6.67 times 10 to the negative 11. Okay, and where do you think these units are derived from? Yeah. If we solved for G, right, it would look like this in this equation. We would say G, we would just switch these two places, right? We'd say G equals F times M1, M2 over R squared, which would give us newtons times Oops, I'm backwards. Yeah, it would be the reciprocal. That's my fault. Okay. Over m1, m2. Okay, so we get newtons times meters squared over kilograms squared. Okay, that's where those units come from. Okay. I'm not really concerned that you have the units, ready to go every time. We're not going to have to plug those in. But the important thing for you to realize is that in order for this constant to work, our other units must match. So we have to have a force in newtons, we have to have our radius in meters, not kilometers, and we have to have our mass in kilograms. Okay? Because if we're dealing with planets, they're probably going to give us our radius in meters, right? Or in kilometers. They're going to say it's this many kilometers away. You need to be able to convert that to meters and then plug it in. Okay? Otherwise, our gravitational constant will not work. Okay, M1, mass of object 1, M2, mass of object 2, usually the mass of the Earth. It doesn't matter which mass is which, okay, because we're just multiplying them. Doesn't matter which one goes first. If we're talking about an object on the Earth's surface, then one of those masses needs to be the mass of the Earth, and I'll give you that value, okay? Okay, this is the basically statement that summarizes that equation and what his ideas were. So I need you to go ahead and have this down into your notes, okay? Read through that, conceptualize it. You can, shorten it down if you want to, but we need to have this part in our notes. Okay, so in this definition, I want you to think about this last sentence and what that means, okay? This force acts along the line joining the two particles. So this says every particle in the universe attracts every other particle. So every single thing in this universe is being attracted kind of to each other, right? You have a gravitational force between you and another person, this desk, whatever it is, you've got a gravitational force between those two objects. The reason we don't start seeing things just like randomly sliding together is because you're also being attracted to the Earth. And the Earth's mass is so much more than the mass of any other object that it basically takes precedence, right? It kind of trumps everything else, okay? So when we have one thing that is so much larger than the other, that's going to be what we're attracted to first, right? That's got to be what's holding us down. So if the Earth's mass wasn't that big, we might randomly start seeing things move together, okay? But the Earth's mass is so big that it basically just takes control, and that's what we're attracted to all the time. That's why gravity keeps us on the ground, okay? So you don't just randomly see things sliding together because they're attracted to the surface of the Earth or the Earth so much that it's not allowing them to move that way, okay? But I want you to think about this. It says, the force acts along the line joining the two particles. So if I have my little person here, okay, I have the little person here, my gravitational force would go basically from the center of each of those people straight across, okay? Our force doesn't do anything crazy. It's not a wave, right? Nothing crazy. It doesn't go to the Earth and then come back. That's not how it goes, okay? I know that seems pretty simplistic, but you need to understand if the gravitational force were enough to pull things together, it would be a straight line motion, okay? That's why when you drop something, it doesn't take like a loop-de-loop path to get to the ground, right? It just falls. Straight line motion between those two things. Okay. Questions there? Okay. Let's try a problem here. 50-kilogram person and a 75-kilogram person are sitting on a bench so that their centers are 50 centimeters apart. What's the magnitude of the gravitational force each person exerts on the other? All right, so let's go ahead and start getting our variables here. Since we're looking at two individual objects, one of the objects is not the mass of the Earth, right? We're looking at both the masses of the people. Gravitational force, so if we set up our our equation here, we'd say big G times M1, M2 over R squared. We're solving here for the force due to gravity. So we'd say Fg equals 6.67 times 10 to the negative 11th. M1 times M2. And what do we need to do with our radius here? Square it, good, but we need to convert it to meters. Okay, so 50 centimeters is how many meters? 0.5, it's a half, right? So if you can do this in your calculator without having to do anything fancy, right? When you do this in your calculator in one swoop, right, without having to re-enter numbers, I would start with the bottom, 0.5 squared, then I would say 50 times 75 divided by answer, and then I take that whole answer times 6.67 times 10 to the negative 11th. Okay, that way you're not having to re-enter numbers. Start with the bottom, and then work your way over.
And then she's like, you need to use it. I was like, okay. Oh, 1 times 10 to the negative 6.
1 times 10 to the negative 6. And what's our units?
The thing, newtons. Newtons. No, not newtons. Yes.
Yeah, we're solving for a force. Newtons. Okay, so we have two people sitting a half a meter apart, and we've got a force that's basically 1 micronewton. Do you think that's enough to pull them together? No. This 50 kilogram person's gravitational force compared to the Earth is 490 newtons. Okay, so 490 divided by 1 times 10 to the 6, negative 6. Okay, that's a lot bigger. Okay, so that magnitude of the gravitational force on the Earth compared to the gravitational force between those is like 1,000,000 times bigger. Okay, or 1,000,000,000 times bigger. I don't even want to count the zeros in my calculator. Okay, it's a lot bigger. That's why we don't see two things start to randomly slide. Okay? Very good.
Are all the numbers going to be small?
When they were 10 meters apart, the distance between them changed and the force became 56 newtons. How far apart were they then? Okay, so we're trying to basically look at the distance and how this radius changed.
Great.
Okay, so let's go ahead and start looking at what we need here. Are we given either mass? No. And we don't necessarily even know if we're looking at the Earth and an object or two other objects. We don't know. Okay, so this is how we need to go ahead and solve for it. We've got the radius at 10. And when the radius equals 10, the gravitational force is equal to what? 14. Okay. So let's go ahead and plug these numbers in. We know 14 equals G. We don't know M1 or M2, but we know R squared, so 10 squared. So let's think about it this way. In between these basically in between these two situations, are the masses going to change? The masses of the object, are they going to change? No. So we can solve for this whole term right here. Right? We're going to be able to solve for the product of those two masses, and then we can plug it into another equation, right? We don't really need to know individually what each one is. As long as we know the product, we can plug that into another one. So let's go ahead and solve for that first. The way we do that, we need to move this over first, and then we'll multiply by that 10 squared. Okay, so 14 divided by G. When you divide by a scientific notation, you need to use the E button, or you need to put it in parentheses. Did we get a pretty big number here?
Yes.
Yeah. So the product of mass 1 times mass 2 is equal to what? 2.1 times 10 to the 13th, right? Okay, so this is M1 times M2. That product is not going to change between the first situation and the second situation. Okay, are we on the same page there? So now we can take that and plug it in to solve for, what are we solving for in the second situation? Yeah, the distance or the radius, good. So our gravitational force becomes 56. Oops. Okay, so algebraically, we need to bring G over first, so we'll divide 56 by 6.67. Okay, and that leaves us with 8.4 times 10 to the 11th equals 2.1 times 10 to the 13th over r squared. Okay, so when our variable's on the bottom, what's the rule? We're going to switch these two places. So we would take 2.1 times 10 to the 13th divided by 8.4 times 10 to the 11th. And after that, what would we need to do finally? We have to remember to square root it because it is r squared. What happened to our forces here? Did we double our force? No, we quadrupled our force. So if we take 56 divided by 14, we get 4. Okay, so that means our force increased by a magnitude of 4. What happened to our radius? It got cut in half. Okay, so there's a relationship here, but it's not just as straightforward as a double leads to a half, right? It's quadruple leads to a half, and it has to do with this r squared. So yes, there is a pattern, not one that we necessarily need to memorize, but yeah, you're right, there is a relationship between those two. Okay, good. Any questions here? Did everyone get that to come out? Okay, very good. So here's a couple constants that we need to know. Okay, so it says, what's the force of gravity acting on a 2,000 kilogram spacecraft when it orbits 2 Earth radii from the center? And I give you the radius of the Earth right here. We'll go through how we plug that in. Okay, but the radius of the Earth is the distance from the Earth's core, the center of the Earth, to the surface. Okay, that's a really important distinction. It's from the Earth's center to the surface. That's important. And then the mass of the Earth we'll have to use a lot, which is 5.98 times 10 to the 24. Those are two constants that I'll always give you. You might want to put them on your equation sheet because we use them a lot. Force of gravity. So we know M1. We'll just call M1 the mass of the Earth. So M1 is 5.98 times 10 to the 24th. M2 is 2,000. G we know. We're solving for FG. But R here, it says 2 Earth's radii from the center. So let's see here. Our Earth. Okay, here is the center of the Earth. This would be the radius of the Earth, right? And it says it's orbiting at 2 Earth's radius. So all we're going to do is basically say it's equal to that distance above the Earth's surface. So this is also happens to be a distance that's the radius of the Earth. Okay, so all that we're going to do is we're going to add those together, and that's going to be our radius. Okay. So the radius means that's going to be 6.38 times 10 to the 6th meters times 2. Yeah, we'll square it when we plug it in. I'm going to leave it regular for right now, but yes. Okay. So we're solving for FG. This chapter you have to use scientific notation a lot. Okay, so just use that E button. And don't forget to square that denominator. Okay. This equation has a lot of room for error because you have to plug in so many big numbers in your calculator. So just take your time. If it's set up like this, I like to start from the bottom and work my way over. Let me give you some more figures here. Okay, mass of the moon, mass of the earth, mass of the sun. Yeah. 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 You don't have to memorize those now.
The sun is 630. E to M.
Okay, so this is what our diagram kind of looks like. The moon is the gray, the earth is the blue, and the yellow is the sun. Okay, so they're at right angles to each other, so they basically form that right angle. That's what that means, okay? Assume the earth and the sun are at right angles. Okay, what's the net force on the moon due to the gravitational attraction between the both earth and the sun? So we're kind of seeing, like, if the moon were to, like, move right here, it would probably be pulled kind of in this direction somewhere, right? If both of these things are pulling on them, it's kind of going to move somewhere like this. So we're going to look and find that net force. We need to basically find the gravitational force between these two objects and the gravitational force between these two objects, and then we'll combine them to find that net force. So let's go ahead and look at between the earth and the moon first. Okay? So I'm going to put this one in blue so we know this one that we're working with the earth. Okay, gravitational force. G. Mass of the earth times the mass of the moon. It is a negative 11, I'm sorry. Don't forget to square that radius. Okay, so for the sun, we'll take big G. Yeah, big G. Mass of the sun, mass of the moon, divided by the radius squared. Listen. Now we're going to take these forces and we're going to add them tail to tip to get the net force. Okay, so let's say that we need to add them tail to tip, so not one right on, or not from the origin. We're going to add them tail to tip, so we'd say, let's see, here's the moon. The Earth's going to pull it this way, the sun is going to pull it this way. Okay, so one of these sides is 1.99 times 10 to the 20th. This side is 4.34 times 10 to the 20th. Our resultant would look something like this. Let's go ahead and solve for that resultant. Remember, with our displacement, we also need to find, or with our net force, we also need to find the angle. What is it? At what?
At 65 degrees.
65 degrees. Not 65, not 65. If it's this angle right here, what is it? Not 45.
65.
Okay, 65 degrees what?
No. Wait, is our axis, like, is it on top?
Our axis is always right here.
Well, but it's touching the east.
No.
So east
Touching the south. East of south. And that's just on our coordinate system. Yeah, that would be a different dimension when we get to space.